Before I get started, I wanted to thank the UNU organization for awarding me a travel grant so I could be here to talk to you guys about this. Okay. So here's a graph that I'm showing you of the distribution of surface Mare deposits with age here on the x-axis. So you're seeing that there's a peak in exposed Mare basalt ages around 3.7 billion years ago. Here I'm showing you in this blue vertical bar the ages of several large impact basins from about Nectaris to Oriental. So you can see that just prior to this peak in exposed Mare basalt ages, you're having a lot of large impact basins. And what I want to investigate and what I'm interested in understanding is the early or ancient volcanic history of the moon. And so I want to begin to address this question of early volcanism by taking a look at this section of time and want to begin to address the question, what does this distribution look prior to this 3.9 billion years ago? Is there a lack of volcanism during this time in lunar history? Was there a slow gradual increase, or was there a lot of volcanic activity during this period of time? And I want to address this by thinking about the distribution and ages of impact basins. Are there is there a lack of volcanic deposits because they weren't there, or because they're being covered up? So here are the main science questions that are driving a lot of this work. I want to understand the global distribution of extrusive volcanic deposits on the moon. Do they have the same distribution as the surface Mare basalts? And I'm also very interested in understanding the mineralogy of these deposits. Do they have a similar mineralogic signature to the exposed Mare basalts, or do they vary or are different in any mineralogy that we can observe in some way? So quickly, I'm going to be saying Cryptomare a lot, which refers to these ancient volcanic deposits. And these are deposits that are typically associated with Nectarin and pre-Nectarin basins. And so you start with these topographic lows that will flood with volcanic deposits and then later be buried by ejecta from large impact events. And so you get this deposit, this buried volcanic deposit that ends up having a higher albedo than you would normally expect for volcanic deposits. So they're buried by high albedo feldspathic impact ejecta, and they can be easily identified by the presence of dark halo impact craters. So dark halo impact craters are small impacts, usually less than 5 kilometers in diameter, that impact into this higher albedo surface, and they excavate lower albedo material. And when you go in with mineralogic information, in this case I'm looking with the moon mineralogy mapper data, so V-near spectral data, you can see that these are actually basalts, and so you're able to identify these buried volcanic deposits. Okay. So here's a list of some of the data sets that I used in this project. I extensively used the Moon Mineralogy Mapper dataset to map these deposits as well as to measure the mineralogy. And in order to identify the mineralogy, I used the modified Gaussian model to better constrain the absorption band centers for the various absorption features found in these spectra. I also used LROC data, Diviner rock abundance, LOLA, both the surface roughness as well as topography data to characterize those deposits that I was able to identify and map. Here is the Moon Mineralogy Mapper optical period 2C1 dataset, and this is shown in RGB form, where R is the 1 micron integrated band depth, the green is the 2 micron integrated band depth, and the blue is the reflectance at 1489 nanometers. So when you look at this map, everything that's orange or yellow represents mafic material. So there's strong pyroxene signatures in the near side and the near side Maria, and SPA, and various other locations on the surface of the moon. And so in order to identify Cryptomare, I started by looking at these larger global mosaics and looking for areas that had strong mafic signatures. And a really good example of one of those is right here. This is the Schiller-Shikard area. It's an extensively studied Cryptomaria. And you can tell that it's got strong mafic signatures. And so an example of how I went about doing this is one of the areas that I mapped. This is that same color mosaic where the yellows represent mafic materials. And here is an example of a dark halo impact crater in the color mosaic. And here are close-ups of that crater in the albedo and also in the color mosaic. So you can see that there's a small deposit, dark halo deposit around that crater, but in the color data it really stands out and you can really see how extensive this is. And when you go and look at the spectra, it's clearly a basaltic, got a basaltic signature, a high calcium pyroxene. So I used the Moon Mineralogy Mapper data to identify the outlines of these deposits, and then I went in with all of those other data sets to try and characterize these ancient volcanic deposits. Do they have a distinct surface roughness? Do they have distinct rock abundance? So I went and did all of that with these data. And I did that for about 30 different locations on the moon. This is a map with all of these red dots showing the location of proposed Cryptomaria. And this comes from a variety of different papers going back all the way to the 70s. People have been looking at this for a long time. And so here are the proposed locations. And here are the locations that I was able to identify. So the Cryptomaria that I mapped are shown in orange here. And you can see something that really stands out is that all of these are very closely associated with exposed Maria. They don't appear on the far side. They're all tightly confined to near side deposits or other deposits on the far side here in SPA, in Austral. But another striking feature, you can see that the largest of these deposits are all associated with ancient impact basins. So here is the Schiller-Zucchius Basin. You have the Balmer-Captain Basin, Smithy, Lomonosov-Fleming. So all of these larger deposits tend to be associated with large pre-Nectaran impact basins. Oh, and I should say that when you calculate the total area of the Cryptomaria that I've been able to map with this project, you increase the total surface area of extruded Maria basalts by about 2%. So you go from something like 16% of the surface is covered with Maria basalts to having about 18% of the surface being covered with Maria basalts with the addition of these deposits. Okay, so I want to talk to you a little bit about the mineralogies that I've been able to identify. Here's an example of some M-cube spectra from dark halo impact craters in the Austral Cryptomaria. You can see that they have the characteristic pyroxene signature, a strong 1 and 2 micron absorption feature. And so I collected spectra of dark halo impact craters for all of the Cryptomaria ponds that I was able to map. I did a continuum removal process and then processed them with the modified Gaussian model to determine the pyroxene mineralogy, specifically looking at the 1 and 2 micron band centers. So here are the results, and I'm showing you them in a 1 micron band center versus a 2 micron band center graph here. And to illustrate this a little bit more clearly, here's the 1 micron band center. So here's my example pyroxene spectrum. The center of the absorption feature at 1 micron is on the y-axis, and then the center of the 2 micron absorption feature is shown here on the x-axis. And when you see this, all of the data, both the Cryptomaria and the exposed Maria, cluster together. And when I was doing this analysis, what I really wanted to do was understand how do Cryptomaria mineralogies compare with exposed Maria in the same region and then also across the moon. So when I was looking in Schiller-Shikard, I collected spectra of the Cryptomaria there as well as the exposed Maria there. And it looks like a cluster right around here. This is on the clinopyroxene, that's reverse. This is a clinopyroxene. Down here are the orthopyroxene band centers. This is the synthetic pyroxene trend that was developed by Rachel Klima. So the data cluster here, but when you take each individual area and you look at them separately, you find some interesting trends. Here are 2 examples of data that are tightly clustered on top of each other. Here are some SPA data. These are the Cryptomaria in orange and the exposed Maria in blue. And you can see that they overlap pretty significantly. The same is true for the marginous exposed Maria and Cryptomaria deposits. In other areas, you have much greater variability. Here is the Schiller-Shikar data as well as West Humorum data, and there still is overlap in the Cryptomaria and exposed Maria, but in this particular case, you see much more variation in the Mari deposits that I've mapped. Okay. Last thing I want to quickly talk about is Cryptomaria ages. And so in this particular case, what I did was I looked at the most extensive Cryptomaria, those that were in the large pre-Nectaran impact basins, and I conducted crater counts on those surfaces, which are shown here. I really want to point out, though, that I'm dating the last resurfacing event. So using this diagram again, I'm dating the last time these deposits were resurfaced. So if I take this histogram, this is the same histogram that I showed you before on the first couple of slides, just stretched out, and this is the impact basin ages. You can see that all of these cluster right around this time of when the largest impact basins were occurring. So a lot of these Cryptomaria in Schiller-Shikard and Smithy and Lomonosov-Fleming are at least as old as sort of 3.8 to 4 billion years old. So I'd like to conclude by saying that the distribution of Mare basalt volcanism does not appear to have changed much since these Cryptomaria were emplaced on the surface. This study has found an additional sort of 2% of the surface covered with Cryptomaria, and that largest increase is seen in the eastern hemisphere of the moon. The most aerially extensive deposits are located in large impact basins, and the Cryptomaria and Maria appear to have similar mineralogies in the same location on the moon. So with that, I'll take any questions.
So this is really neat stuff. My recollection from older papers is that Graham Ryder was always looking for the oldest Cryptomaria, and he was looking for little clasts that were maybe in breccias we had from older samples and the rest. I don't remember what ages that material, if they found any, and what material or what ages it had. I think it was very, very limited, which would suggest we wouldn't have a lot of ancient Cryptomaria. But do you have a comment on that?
Yeah. So there was one paper by Larry Taylor, I think, in 1983 or 4, where he found a basaltic class that was about 4.2 billion years old. And then there was a recent paper in 2009 by Terada, Kalahari 009, a meteorite, and they also found what they thought was a Cryptomaria class. It was a very low titanium basalt that was also around 4.2 billion years old. So there has been some evidence, but not a lot in the sample collection.
Clive Neal, Notre Dame. Nice work, but I came in late and missed the beginning, so you may have covered this. You sort of did at the end. Where you found these large Cryptomaria in basins, could they be impact melts rather than actual Mare volcanism?
Well, I think that the evidence, especially the mineralogic evidence, suggests that they are probably basalts that have been extruded as opposed to impact melts. A lot of that has to do with the lower albedos, the mineralogies that are very similar to exposed Mare basalts that are younger in the same area. So that leads me to think that they're probably extruded products. They generally have smooth surfaces that have been covered and appear very similar in morphology, minus the high albedos, to basalts that you would see in the other near side.
Just a cautionary tale, because 14310 was a basalt, and it was a Mare basalt until 1974, 75. Now it's an impact melt. It looks very much like a Mare basalt.
Okay.
Impact melts from LRO show very smooth surfaces in some of the recent ones anyway. And again, I think Cryptomaria may have been found in Breccia 14321, 4.24 billion year ages of some of those basaltic clasts. But the connection still needs to be made, and maybe we need more samples. So
I would not be opposed to that idea. Thank you. Thank you.